Greetings, my name is Louis Hong. We are Group 4 from Section 2 of Chemical Engineering Thermodynamics course. We are going to present our project, Separation of Hexane-Octane Mixture. Our project aims to design a flash distillation system to separate a hexane-octane mixture by partially vaporizing the liquid. In flash distillation, a liquid mixture is partially vaporized. The vapor is allowed to come to equilibrium with the liquid, and the vapor-liquid phases are then separated. The two components of the mixture are separated using the fact that they have different boiling points. The component that has a lower boiling point will exist in greater quantity in the vapor phase, while the component with a higher boiling point will exist in greater quantity in the liquid phase. A little bit of background. In real-world industrial processes, the separation of hexane and octane is usually found in oil refineries. Crude oil needs to be distilled to separate the numerous types of hydrocarbons found within it, including hexane and octane. Many industrial distillation processes involve the separation of more than two components.
Hello, my name is Calvin, and next I will be explaining typical operation conditions found in flash distillation columns. In general, industrial distillation temperatures vary widely depending on the substance. One of the substances that can be taken as an example is crude oil, which is a naturally occurring and unrefined liquid fossil fuel. When undergoing distillation, crude oil can be separated into many distillates, with the most popular being petrol and diesel for vehicles with engines that run on fuel, or kerosene, which is used as fuel for cooking in developing countries. These products are obtained at varying ranges of temperature from as high as 600 degrees Celsius to as low as 25 degrees Celsius. But in this project's case, we will be setting the operation to a temperature of 87.8 degrees Celsius and pressure at 100 kilopascals. Moving on, this project involves on binary distillation, where only one tower is used to separate both hexane and octane as shown in the process diagram. Using equilibrium data, equilibrium calculations are used to obtain the boiling point and equilibrium vapor and liquid composition, which is then used to calculate the output stream composition.
For this part, we will go over the input data and assumptions. We get 100 mole mixture input to flash separator consisting 0.7 mole hexane over mole and 0.3 mole octane over mole at a temperature 87.8 degrees Celsius. The table on the right shows the Octane constant for hexane and octane that we obtained from table B.2 in Smith et al. 2022. For hexane, A is 13.8193 and B is 2696.04 and C is 224317, and for octane, A is 13.9346 and B is 3123.13 and C is 209.635. The following assumptions are made for the flash calculation. First, this is ideal solution. Second, the system is at steady state. And third, the flash drum is adiabatic. Next, we move to the calculation part. First, we find P saturation using Octane equation. Learn P saturation equals to A minus B over T in degrees Celsius plus C. Then we will get P saturation hexane equals to 177.9317 kPa and P saturation octane equals to 31.0128 kPa. After we get the P saturation, we can calculate bubble pressure, where P1 saturation equals to P saturation hexane and P2 saturation equals to P saturation octane. P bubble equals to X1 times P1 saturation plus X2 times P2 saturations, and P bubble equals to 133.8560 kPa. And after we get the bubble pressure, we can calculate dew pressure, P dew, where P dew equals to 1 over Y1 over P1 saturation plus Y2 over P2 saturation. So P dew equals to 73.4888 kPa. Then after that, We can use Rod's law to find equilibrium ratio or Ki. Ki equals to Pi saturation equals to P, where we use P equals to 100 kPa, where P is between P bubble and P dew. So K for hexane equals to 1.7793 and K for octane equals to 0.3101. And after that, we can calculate moles of vapor, V, and moles of liquid, L. Let V plus L equals to 1. Summation Zi times Ki over 1 plus V bracket Ki minus 1 equals to 1. We will get V equals to 0.6293 mole of vapor. And since we have 100 mole of mixture at inlet stream, we times it with V. So V will be 62.93 mole of vapor. And by using material balance, we will get L equals to 100 minus 62.93. And L equals to 37.07 mole of liquid.
Next, move to the vapor phase mole fractions. As you can see from the equation derived from the phase calculations using our given feed compositions and K value, we determine that the vapor phase will be approximately 0.8357 hexanes. Since this is a binary system, the remainder about 0.1643 will be obtained in the vapor phase. These calculations tell us how much of each component prefer to be in the gas forms. Next, move to the liquid phase mole fractions. The K value which represents the equilibrium ratio is the key here. By rearranging the K value definitions, we can easily calculate the liquid phase mole fraction for each component. For hexanes, we find it make up roughly 0.4697 of the liquids, and for the octane, the balance means it constitutes about 0.5303 of the liquid phase. Next, move to the discussion and analysis. Let's begin with the PXY diagram. In this diagram, we have pressure on the y-axis and mole fraction of hexane on the x-axis. Since our system is operating at 100 kPa, we draw a horizontal line at the pressure. This line intersects both the liquid curve Px and the vapor curve Py. The intersection with the liquid curve tells us the compositions of the liquid when it starts to boil. This is known as the bubble point. The intersection with the vapor curve tells us the compositions of the vapor that forms, known as the dew points. From the graph, we can see that at 100 kPa for a certain mixture says around 50% hexanes, and the vapor that forms contains a higher mole fraction of hexanes, approximately 80%. This shows that hexane is more volatile and tends to move into the vapor more easily than octane. This is the basic principle behind distillation. The vapor is rich in the more volatile component, which is hexane in this case. Now, let's look at the TXY diagram. In this graph, temperature is on the y-axis and again, mole fraction of hexane is on the x-axis. Since our system is at 87.8 degrees C, we draw a horizontal line at the temperatures. Just like before, this line intersects the liquid line Tx and the vapor line Ty. At the temperatures, we also in the two-phase regions, which means the system contains both liquid and vapor in equilibrium. From the graph, we can observe the same behavior. The liquid phase is rich in the octane and the vapor phase is rich in hexane. So at 87.8 degrees C and 100 kPa, we can partially vaporize the liquid mixture, then condense the vapor to collect more hexane. This is how the separation is achieved, using the difference in volatility clearly shown by the gap between the two curves on both diagrams. In conclusion, our flash separation successfully achieved an effective split based on volatility. The vapor phase is about 83.6% hexane and the liquid phase is roughly 53% octane. For future process design, 100 kPa is a good balance. If we need higher purity, multi-stage flash or distillation are the next steps. And critically, continuous monitoring of the feed composition is essential, as even small changes can significantly impact our separation performance.